Introduction to Transactions and Concurrency Control. This is our familiar diagram of an architecture of a database management system, and I'm happy to say we've covered it from the top to the bottom, all the way from the SQL language, which is declarative and just expresses the intent of the user, down to the location of bits on disk in the disk space management system, and everything in between. And this picture is fully functional, and you could build a database management system based on what you've learned so far. The limitation would be that that is a database management system that only runs one query at a time and isn't necessarily very reliable. So in the next set of lectures, we're going to expand our scope to consider what happens when we have multiple clients running SQL at the same time over a database that we really want to make sure is fault tolerant and reliable in every way. And we are now going to study this component of the database, which is the transaction manager. There are two subcomponents in the transaction manager. One is a lock manager, which is going to handle concurrency control issues, and the other is a logging and recovery manager, which is going to be responsible for fault tolerance and recovery. I want to remind you before we go on that virtually every application you can think of these days runs on top of a database system if it manages state of any kind. This is everything from your ride-sharing apps to your airline travel apps to your retail to your banking and even gaming. All of these systems, if they have to manage the state of the world, they are probably using a database system down below. And these systems that you're looking at, these applications, have to run 24/7 around the globe and be reliable. So those are the requirements we need. They can never lose data, they have to keep working, and basically people depend on this stuff all around the world. Every application that's connecting to the database wants something from it. Of course, they want to be able to run queries and do updates, and that's the stuff we've learned so far. But real applications are not simple queries. They're composed of multiple statements being generated by users who are taking behaviors in their applications, and those behaviors are being translated down to SQL statements, maybe multiple SQL statements down below. And then typically there's many users using the database via the application at the same time, perhaps via multiple applications on the same database. Okay, so there's all these SQL queries streaming in and all these answers streaming out all at the same time over long periods of time. So the system has to handle all those multiple users and it has to stay up and be correct. So when we talk about concurrency control and recovery, we're going to talk about two main components, as I said. The first is concurrency control. And here the goal is to have correct and fast data access in the presence of concurrent work by many users. Many users hitting the database at the same time. We want to make sure that the results that they observe make sense and go fast. And all this is happening in the face of disorderly processing. Things are coming in, they're not necessarily being run in any particular order, but we want to provide the illusion to the programmer that their program is running in a familiar, ordered way. So that's going to be our challenge. For recovery, which is the second part, we have to ensure that the database tolerates faults, and it's not going to be corrupted by bugs in application software, by bugs in the system software, or by failure of the database disk media. Okay, and this storage that people put databases on is being used for the mission critical data. If it's going in the database, it's probably important, and therefore we really have to do a good job making sure that data is reliable and recoverable after failure. And notice that really what these guarantees are, correctness, speed, recoverability, are all about providing contracts to the application programmer. In essence, the database management system is providing guarantees so the application programmer doesn't have to worry. This lightens the load of the app writers. They don't have to think about these issues. They just write the logic for their application and let the database handle issues like the ones we're going to learn about next. Now, we're going to mostly talk about concurrency in this first lecture, and you might start by asking a very natural question. Why bother letting multiple queries run at the same time? Why not run the queries one at a time really fast? It's the same computer. It's going to handle the same number of queries no matter what. Why not just queue them up and run them one at a time? Well, there's two advantages to allowing concurrency in the database. The first is throughput. We're going to be able to do more transactions per second if we run multiple queries at the same time. Why? Because we're going to increase the utilization of our disks and our processors. The basic idea is that there's parallelism even in the simplest of computers running a database. So take a single core computer, a computer with one CPU that can only execute one sequence of instructions at a time. It can run while its disk drive is going and reading or writing data. So there's already parallelism between a single core and the disk drive. And by having multiple queries run at once, we can keep the disk and the CPU busy at the same time, increasing throughput. Of course, most computers, even your laptop today, even your phone, are multi-core computers. They actually can run multiple sequences of instructions at the same time in the CPU or in multiple CPUs. And so what we want to see here is we want to see the system scale up and run as many queries as there are cores or CPUs in the system. Okay, so multi-core systems should certainly be running in parallel, doing multiple transactions at the same time. There's a whole other reason we want to do concurrency, and that's latency, which is the average response time per transaction. Multiple transactions run at the same time. That means that one transaction is not necessarily dependent on the time it takes to complete another. If you queue everybody up in the same line at the grocery store and somebody really slow is in the front, everybody waits. If you have multiple tellers at the grocery store, odds are good that some people will be getting through the lines pretty quickly, and the occasional slow person will only affect a few people behind them. So one transaction's latency should not be dependent on an unrelated transaction. That's the hope. And so by having concurrency, we're going to allow multiple transactions to run at once, and the quick ones will go around the slow ones using other resources. So both these arguments are important, the throughput argument and the latency argument. Throughput because we want our system to be efficient. We want it to do a lot of work for a small amount of hardware cost. And latency because we don't want any one transaction to wait for very long. We want the system to be responsive and run at about the speed we'd expect even as we increase the load and run more queries at the same time.